Case 1, b squared minus 4ac is greater than 0. In this case, the roots r sub 1 and r sub 2 of the auxiliary equation are real and distinct. So y sub 1 equals e to the power r sub 1 x, and y sub 2 equals e to the power r sub 2 x are two linearly independent solutions of equation 5. Note that e to the power r sub 2 x is not a constant multiple of e to the power r sub 1 x. Therefore, by theorem 4, we have the following fact. Equation 8. If the roots r sub 1 and r sub 2 of the auxiliary equation a times r squared plus b times r plus c equal 0 are real and unequal, and the general solution of a times y double prime plus b times y prime plus c times y equals 0 is y equals c sub 1 times e to the power r sub 1 x plus c sub 2 times e to the power r sub 2 x. Sidebar: in figure 1, the graphs of the basic solutions f of x equals e to the power 2x and g of x equals e to the power negative 3x of the differential equation in example 1 are shown in blue and red respectively. Some of the other solutions, linear combinations of f and g, are shown in black. You have figure 1. Back to the text. Example 1. Solve the equation y double prime plus y prime minus 6y equals 0. Solution: the auxiliary equation is r squared plus r minus 6 equals open r minus 2 close open r plus 3 close equals 0, whose roots are r equals 2, negative 3. Therefore, by equation 8, the general solution of the given differential equation is y equals c sub 1 times e to the power 2x plus c sub 2 times e to the power negative 3x. We could verify that this is indeed a solution by differentiating and substituting into the differential equation. Example 2. Solve the second derivative of y with respect to x plus the derivative of y with respect to x minus y equals 0. Solution: to solve the auxiliary equation 3r squared plus r minus 1 equals 0, we use the quadratic formula. R equals negative 1 plus or minus the square root of 13 over 6. Since the roots are real and distinct, the general solution is y equals c sub 1 times e to the power open negative 1 plus the square root of 13 close times x over 6, and that's also part of the exponent, plus c sub 2 times e to the power open negative 1 minus the square root of 13 close x over 6. Case 2. b squared minus 4ac equals 0. In this case, r sub 1 and r sub 2, that is, the roots of the auxiliary equation, are real and equal. Let's denote by r the common value of r sub 1 and r sub 2. Then from equation 7, we have equation 9. R equals negative b over 2a. So 2ar plus b equals 0. We know that y sub 1 equals e to the power rx is one solution of equation 5. We now verify that y sub 2 equals x times e to the power rx is also a solution. A times the second derivative of y sub 2 plus b times the first derivative of y sub 2 plus c times y sub 2 equals a times open 2 times r times e to the power rx plus r squared times x times e to the power rx close plus b times open e to the power rx plus r times x times e to the power rx close plus c times x times e to the power rx equals open 2ar plus b close times e to the power rx plus open a times plus restarting that line equals open 2ar plus b close times e to the power rx plus open a r squared plus b r plus c close times x times e to the power rx equals 0 times open e to the power rx close plus 0 times open x times e to the power rx close equals 0. In the first term 2ar plus b equals 0 by equations 9. In the second term, a times r squared plus b times r plus c equals 0 because r is a root of the auxiliary equation. Since y sub 1 equals e to the power rx and y sub 2 equals x times e to the power rx are linearly independent solutions, Theorem 4 provides us with the general solution. Equation 10. If the auxiliary equation a times r squared plus b times r plus c equals 0 has only one real root r, then the general solution a times y double prime plus b times y prime plus c times y equals 0 is y equals c sub 1 times e to the power rx plus c sub 2 times x times e to the power rx.